Let's talk about our ESP32 S3. This microcontroller in particular, so that's the ESP32, is a dual-core system, which is somebody who grew up with a single-core desktop machine. This sort of blows my mind. And it's running at 240 megahertz, which is pretty fast for a microcontroller. You can compare that to something like your standard Arduino, which I believe are more in the range of 8 megahertz. This microcontroller has a cache. So for those of you in computer systems, some of these things probably will sound familiar. It has an instruction dedicated cache and a second cache dedicated to data. Each cache is 4-way set associative, and it uses 16-byte blocks. There are slight differences depending on which version of the ESP32 S3 that the company Seed Studio we purchased these from uses, and I couldn't find out exactly if they were using the 16-byte block size or the 32-byte block size. It's not going to matter that much for our programming needs, though. Our microcontroller on the chip itself has a 384 kilobyte ROM and 512 kilobytes of SRAM. So you could think of this as long-term storage. For the most part, our programs will be uploaded into ROM, so they need to be under this 384 kilobyte size. RAM is the short-term stuff. You could think of this as, if you've ever seen the picture of a stack growing down toward a heap, you could think of this as what is done inside of your RAM. In addition to this, the ROM and RAM on the chip itself, sort of right next to the processing units, like the ALU, the arithmetic logic unit, you'll have access to an additional 8 megabytes of PSRAM and 8 megabytes of flash. So this flash memory's long-term storage is similar to the flash memory on your phones or the flash USB sticks that you might have. PSRAM is what's called pseudo-static random access memory, RAM. So it really is grouped in as sort of an additional bucket of RAM that your program can use if you need that extra bit of space. This next intimidating figure here is essentially a summary of all the functionality that's available to you on the ESP32 S3. As I mentioned, right there on the chip itself you have the CPU and memory, so that's where you'll find the cache and that smaller bit of SRAM and ROM that I mentioned. In addition to that, there's something called JTAG. That hopefully won't be too something we won't interact with too much this semester. It's a debugging interface. It's not really useful to go through this entire diagram, but I will highlight some of the things that are on this chip that you might find interesting. On the chip, you'll find a USB communication device. You'll find UART, so that's universal serial interface. You'll also see mention of PWM and I2C. Those are communication interfaces that we'll be using for, in the case of PWM, the motor driver, and in case of I2C, many of the peripherals that we'll be using. Peripherals is essentially the name of anything that's not part of the main chip's functionality. It's not part of sort of this core part here. We'll also be using GPIO and the Wi-Fi modules that are built into the chip. It's worth mentioning a few of these in just a little bit more detail. If you recall our motor driver, I'll show just a few of the pertinent chips here. It's going to have, a few of the pertinent pins. It's going to have, for controlling one motor, one pin that we control using PWM to control the speed of the motor, and another one that uses GPIO to control the direction of the motor. So you could think of those as being sort of tied into these couple of banks that we see on the chip's interface. And of course that's just the control side. On the other side we'll have outputs, and those were I think called mout1, and mout2, motor out 1 and motor out 2. And there's an A motor and a B motor, both on the input side and on the output side. We haven't discussed it much yet, but our chip has a lot of different peripherals that are tied directly into this I2C interface. The I2C, I2C interface has 2 pins that are used. There's one for SDA, that's the data pin, and one for SCL, that's the clock pin. And tied into those, we'll have several peripherals. Our OLED display is connected over I2C. Our compass will be. Our inertial measurement unit will be. The vision module also is over I2C. So the normal way to draw this would be as a bus. Hopefully you'll forgive me for not showing you the cleanup there. Each module will be connected to both lines. And they all have their own unique addresses so that we can differentiate among them. So for example, on our program we might say, hey, anything on the I2C interface with the address 0xAF, and let's say that's the OLED display. This next message being broadcast is specifically for you, and the rest of the devices will just ignore whatever comes after and wait until they see something that's addressed to them. The final module here worth remembering is the wireless communication, the Wi-Fi module. And I'll try to remind you of just a few of the most important parts of it. We have our thread of execution. And as part of it, we start listening. So there'll be a call to listen at some early stage in your program. When we are listening, at that point we can do something like display the IP address and port, so that you can look those up and plug them into the browser widget that I have as part of the code for this course. And then you'll have a signal that gets received by our Wi-Fi module that there was an opened connection. What you do with the open connection is sort of up to you at that point. At this point, it's probably worth doing something like enabling motors. Maybe not starting them, but just saying that they can be started. And of course, the way that we're coding up our communication is we'll have a sequence of heartbeats. So that we know no communication has been lost. And after a certain timeout, we'll make sure to disable the motors. We could also disable the LiDAR and disable other systems. There's not much risk of leaving those running though. The biggest annoyance there would be that they just draw power when they don't need to be. And there's more to it than this. And somewhere in here we could, if we wanted to, send a packet of data. So for example, the motor speeds. We could send that out and be read on the web browser side to display data. For example, you could have a plot that updates over time. And again, for those of you who have taken CS 105, so the computer systems course, or any other operating systems course, this picture might look familiar to you. I really have it here just sort of a way to comfort those that have seen it before. The microcontroller really does run a similar sort of fake memory model as your laptops and desktops do. That is to say, it's really backed by virtual memory, but the picture you should have in your head looks something like this. where you have some high memory address, and that's where you'll find data that's on your stack. That's going to grow down as you do things like call functions. And anytime you dynamically allocate something, for example a list, by calling malloc, you're going to grow your heap space. And just like a process you might have running on your computer, you can have uninitialized global variables, initialized global variables, and then of course you're always going to have the code that you're actually executing. That has to exist somewhere in memory as well. Slightly different from the picture you might be used to is we can denote a difference between external and internal memory. It's true on your processor, you might talk about in 105 that your processor has a cache, but normally we would group the rest of this sort of up with external memory, or just put the whole thing together. Here on your microcontroller, it's going to make sense to sort of have this dividing line between the external memory and the internal memory. And that's a good place to wrap up this video. In the next video, we'll start talking about what actually happens when you start your microcontroller.